So let's talk about the Tarski's World Worksheet. So we're going to negate these statements, right?
Mhm.
So let's start with the first statement. We don't even need to see the picture to do the negations, right? So it's the worksheet number 1. So problem 1A. So the first statement is a there exists statement. There exists a Z such that circle Z and black Z, right? So let's just read that statement. There exists a Z such that circle Z and black Z. So it says there is an object Z that is both a circle and black. Okay.
Yep.
All right. So let's look at the negation. So for part 1, we're going to write the negation. So the first thing we do is we just put a not in front of the whole thing. And then we're going to bring the not through. And we're going to use what we've learned about negating there exists statement, right? And we're going to use what we learned about negating the predicate. This is the predicate, and it's just P of X, P of Z, actually. Okay. So when we bring the not through the there exists, what happens?
It turns into a for all.
It turns into a for all. So it's a for all Z. It's not true that P of Z. In other words, it's not true that circle Z and black Z, right?
Yeah, I thought it was circle X black C.
Did I write X there? I should have written Z here.
Okay, excuse me.
No problem. That was my error. Thank you. All right, great. So now we've got one more step and we'll be done because we just need to bring this not through that predicate, which is a compound predicate. It's an and statement, right? So we use De Morgan's law. So De Morgan's law tells us about how to negate an and statement. What happens to the and?
The and changes to a or.
That's right. And then we negate both of the components. So not circle Z and not black Z. Or, excuse me, not black Z. So the point is, one of these is true and the other is false because they're negations of each other. They have opposite truth values, right? So either it's true that there is a circle that's also black, right? Or for every object, either it's not a circle or it's not black. So in part 2, when we try to figure out if the original is true or false, sometimes it's easier just to look at the original. Sometimes it's easier to look at the negation. But if you just look at this figure, so 2 isn't part of what we have to do, but we can just talk about it. Does there exist an object Z that is a circle and is black in this figure?
And figure 2.
Thank you. Guess we better look at the figure, huh? No, yeah, figure 1. Does there exist an object that is a circle and is black?
Yes.
And so what Z would that be? What is Z?
Would it be, are you talking about the whole statement or just a circle?
I'm just saying we've got to find a Z that exists that satisfies this. What would Z have to what value would Z take? Which of these objects is the Z?
It would take J.
Yeah, when Z is J, this is true because circle J is true and black J is true. So that's sort of a sneak preview to part 2. This original is true because there does exist an object Z, namely Z equals J, okay?
Okay.
But we don't need to do that. We're gonna talk about that tomorrow in class, so we can go to number 2. So 2 is an interesting one because it's very compound and nested. There exists a T such that, it's double parentheses, triangle T or circle T and gray T. So we're gonna negate that. Hang on, I gotta turn something off. I got something turned on off here. Burn my toast. Hold on. Nothing like burnt toast. All right, so we're gonna negate that. Actually, this is B. This isn't 2, it's B. All right, so we're gonna do the negation. 1. So we can naively start by simply putting the not in front of the whole thing. It's not true that there exists a T such that triangle T or circle T and gray T. All right, so now our job is to bring that negation through. Because this whole thing now is our P of Z. P of T, actually. So when we bring the not through that there exists, what happens to it?
It turned into a for all.
So for all T, it's not true that P of T's. It's not true that triangle T or circle T. So we just sort of do it naively, just using the rules that we understand, and gray T. Now, we have an and we have an or. But the and is the last operator that would be executed. This or would happen first. So it's this and this, okay? So the first thing we do is we bring the not through the and statement. So for all T, not triangle T or circle T, what happens to the and when we bring the not through an and?
It turns to or.
Yep. And then we negate gray T.
So why does the or stay the same?
Because we haven't brought the not through this yet. We're doing that in the next step. You see, the not is being applied to this and this. So we negate the first component, flip the and to an or, and negate the second component. So I've just underlined the 2 components that go with the and. You see what I mean? Now this is a compound component. So the not gets applied to each component, right? So it's not triangle T or circle T, or it's not gray T. Now we bring the not through the this or. You see what I mean? Like we're doing it in two steps. First, we bring the not through the and then we'll bring the not through the or. Why did we bring the not through the and first? Because the way these parentheses are written, we understand this is grouped together, anded with gray T. You see what I mean? This is one component being anded with gray T. So we negate that component, flip the and to an or, and negate the gray T. It's the other component. You see what I mean? That's why we haven't touched this yet. Because the first thing that we did was negate this, which is an and statement. Now we bring the not through the or that's in this compound component, you see? So for all T, when we bring the not through this or, it's going to flip it to an and we negate these two components. So it's not triangle T and not circle T. So that's all together. This is still or, not gray T. Does that make sense?
Yeah.
Okay, so this is a complicated statement. The original was a complicated statement. But what it says is that there exists a triangle T, an object T, excuse me, that satisfies this and satisfies that. See what I mean? So we're looking for a triangle T, oh, excuse me, an object T that is gray and it's either a triangle or a circle. So when we get ready to try to figure out, if it's true, we can look here and we're looking for an object T. It's gonna have to be gray, so it's either gonna be B or D or G, because those are the three gray objects, right? T's gotta be gray. Well, the only gray objects are B, D, and G. A is supposed to be white. It's got some little marks on there, but it's not shaded. It's white. And object T has to be a triangle or a circle. Well, here are our three gray objects. Are any of them triangles or circles?
No.
Nope. So this statement's going to be false, because there is no object T that is both gray and a triangle or a circle. In other words, for every object T, it's either not gray. I'm looking at that first because it's easier. The or doesn't care. We could put these in the other order. For every object T, either it's not gray, and that's everything except B, D, and J, A, C, E, F, H, I, J, and K are not gray, or the object is both not a triangle and not a circle. And that's true for B, D, and G. These objects are not triangles and they're not circles. So the negation is actually what's true. The original is actually false. Does that make sense?
Yeah, it does.
Good. Let's look at the next one. All right, the next statement is a for all statement. It says for all x, square x, or right of xd. So let's just think about what that says. It says for every object X, either X is a square or X is to the right of object D. We can even look at the figure. We can kind of like do a sneak preview and see if we can figure out if that's true just by understanding it. For every X, we check each X one by one. So like we'd start with object A. When X is A a square? No, but we have an or here. Or when X is A, is right of AD true? Is A to the right of D?
No,
Why not?
it's on the left.
A is on the right of D. Right is that way, left is that way. X
A,
is,
okay, excuse me. That's
yeah,
me.
see it? Yeah, the other right. I do that all the time. So it works for when X is A, because A satisfies right of AD. So it works for A, but it's got to work for every X. So now we check B. When X is B, does B satisfy square B or right of BD? Remember, this is inclusive. It could satisfy both, and that would be fine. Sure. Isn't B a square?
Yeah,
So it'll satisfy this predicate when X is B. You know, when X is B, this is true. So it worked for A because A is to the right of D, and it worked for B because B is a square. And it's also to the right of D. So, you know, both of these are actually true for X equals B. Great, so far so good. Has to work for every single X though. So now let's check the next X. The next X is C. I'm just doing them in alphabetical order. When X is C, square C or right of CD has to be true. In other words, C has to be a square or C has to be to the right of object D. C is not a square, okay? But is right of CD true? Is C to the right of D?
yeah,
Yeah. Remember, when we see right of XD, the way we interpret that is X is to the right of D. And so when X is C, sure enough, C is to the right of D. So this statement is true when X is C. Great, we keep going. D. So when X is D, we need to check square D or right of DD. So either square D has to be true or right of DD has to be true or both. So is this predicate true for X equals D?
yes.
Sure. Why? What part of this is true when X is D?
The right of X, just to the right of X.
When X is D, you're saying right of DD is true? Is D to the right of D?
No,
No. Right of DD fails. But what about square D? Is D a square?
yeah,
So this predicate is true when X is D because square D is actually true. So we've checked, so far we've checked it. It works when X is A, when X is B, when X is C, when X is D. It's going to have to work for every single X. So we just keep checking each one of these and let them be X. When X is E, is square E true or right of ED? Yeah, right of ED is true because E is to the right of D. So it works when X is E. What about when X is F? Is square F or right of FD true?
No,
Why not? Square F isn't true?
no, because it's under D.
It's, yeah, right of FD is false. That's true. That is correct. Right of FD fails. But what about square F? Isn't F a square?
Yeah,
So square F is true. So this or statement is true when X is F because square F is true. You see, it's an or statement. Both of these don't have to be true. It's enough if one of these components is true because it's an or statement. And when X is F, square F is true. So the statement is true for X equals F. It's true for X equals G because G is a square. In fact, it's true for X equals H because right of HD is true. It's going to be true for I because square I is true and right of ID is true. It's going to be true for J. J is not a square, but right of JD is true because J is to the right of D, excuse me. J is to the right of D. Did I have I been saying F? It's supposed to be D. My point is, and we can go over this again, no matter which X you pick, for every single X, you can check this predicate is true. Because for every object, either the object is a square, like B and D and F and G and I, or X is to the right of object D. See, all these objects, A, B, C, E, G, H, I, J, K, all of them are to the right of D. So when X is any of these, except for D and F, right of XD is true. So for these X's, it works. But it also is true for X equals D and X equals F, not because right of DD is true and not because right of FD is true, but because square D is true and square F is true. So anyway, that's sort of a sneak preview. Let's write the negation. Because we're going to go over this again tomorrow. This is, figuring out the truth value can be kind of tricky, but let's just naively write the negation. So we're going to put a not in front of this entire statement for all X, square X, or right of D. I don't know what, excuse me, I keep calling that F, it's D, or right of XD. All right, so when we bring this negation through this statement, this is our predicate, this is our P of XD, and then there's our quantifier. So what happens to the for all X when we bring this not through here?
it turns into a there exists.
Sure does. There exists an X such that, and then the not gets applied to the predicate. So it's not in front of square X or right of XD. All right, we're not quite done because now this not is sitting outside this or operated statement. So to bring it all the way through the statement, we have to distribute it across this. So what happens? What is the negation of square X or right of XD? You tell me.
It would be a negation square X
Okay, not square X, good.
and negation right of parentheses XD.
Exactly. Very good. De Morgan's law at work. Let's look at the next. The next one is an if then. This next statement is for all y, white y implies below YA. So we're going to be negating that. So, I mean, first we just stick a knot in front of the whole thing, and then we'll bring it, oh, it's not an X, it's a Y. We're going to bring it through the whole thing. Remember, every if-then statement is a universal statement. And we see that here. It's an if-then statement, and it's universal. So this goes with this, and this one needs this one, and this one needs this one. Okay. All right, so let's bring the negation through. What happens to for all y when we bring the negation through?
It doesn't show there exists.
Sure, there exists a y. And then we get to negate the if-then. White y implies below YA, which means object Y is below object A. A is a particular object. It is this object. Y is a variable. All right, so we've got one more step. We got to bring this knot through this if-then. This is an if P, then Q, right? We're going to have to bring the knot through an if P, then Q. Do you remember how to negate an if P, then Q?
It would be, should I just read the whole statement?
Sure.
It would be negation, parentheses, white y, and not below parentheses, y, comma, a, close parentheses.
Not quite. You gotta recall this, that when we negate if P, then Q, what we get is that P happened and Q did not follow. See, because if P, then Q says if P is true, then Q must follow. Well, if it's not true that P implies Q, then P happened and Q did not follow. That's what P and not Q means. It means P is true and Q is not. So this hypothesis, white Y, that's our P, that does not get negated. You just keep the P. And, but not Q. Well, this is our Q, so and not below YA. Does that make sense?
Yep.
Right? It's P and not Q. So yeah, we did need parentheses because the whole thing is being quantified with there exists. Sometimes it's easier to figure out if an existent statement is true than a universal statement. But not always. I mean, if we just look at this original statement, it says for every object X, if the object, oh, excuse me, for every object Y, if the object Y is white, then Y is below object A. So let's just look at the objects and see if it's true that if the object is white, then it's below object A. So what are the white objects in this Tarski's world? Which ones are the white ones? We have to look at those.
C, H, I, and K. That's what I see.
A is also white.
Okay. A too. So I see A, C, H, I, and K.
Correct. Those are the white objects. A, C, H, I, and K. So for this to be true, this original statement, for every single y, if it's white, then it has to be below A. But A itself is white, right? This says if the object's white, if y is white, then y has to be below object A. Well, A is white. Is A below A?
No.
No. So this statement is false because it fails for y equals A. It has to work for every single y. That if that y is white, then that y is below A, and it fails. In other words, there exists a y that is white and such that y is not below A. And that y that exists is y equals A. It is white and not below AA is true because A is not below itself. See what I mean?
Yeah.
So to disprove this original, we're actually proving the negation. We're finding a y that exists that satisfies white y and not below YA, namely y equals A. So that'll be the way that we will evaluate the truth of the original statement. We'll figure out that it's false because we'll actually say because the negation is true, because when y is A, white y is true and not below AA is also true. So this whole thing is true for the y that exists, namely y equals A. You feel like now you can work through some of the problem?
Yeah, I think I can work through number 2.
Great, because we've got an and statement. We've got just a super simple statement here. It's not even compound. Here's a there exists for all statement. So we'll have to see, this is a there exists, right? And we learned today that or yesterday, when we negate a there exists, we'll get a for all, won't we? And then this gets negated. By the way, when you negate not same shape XY, what's not same shape XY going to turn out to be?
Is it going to turn into just regular same shape XY?
It sure is. That's exactly what's going to happen. The double knots cancel each other out. Kind of like multiplying a -1 times a -1. The negatives cancel out and get a positive. By the way, when we negate x is not equal to y, what do you think we're going to get?
Will we get X equals Y?
You sure will. Good job. So you can bring the not through this and just change it to x equals y, instead of leaving the not outside of x is not equal to y.
I have a question about G. I was confused about that.
Okay,
How would it be read formally?
pardon?
How would G be read formally?
There exists an x such that for all z, x equals z or above xz. So there exists an x such that for all z. The phrase such that follows the there exists to make it sound right. So you can think of it, there exists an x with the property that for all z, but we just say such that. There exists an x such that for all z, x equals z or above xz. Does that help?
Yeah.
Like here, there exists an x, there exists a y such that same color xy and not same shape xy. So we use the phrase such that, after this last exists. Here, there's only one of them, so we say the such that in between, that there exists an x and the all z. There exists an x such that for all z. Like here, we would read this one, for all X, there exists a Y such that same shape XY and same color XY. We would read this one very similarly. For all X, there exists a Y such that blah, 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 blah.
Okay. And if we were talking about X and Y, would it just be like, say for example, E, it says there exists an X and there exists a Y such that the same color of X and Y and not the same shape of X and Y?
Yeah, we usually don't use the word of. We usually just say same color XY and not same shape XY. Or you could read it like this. X is the same color as Y and X is not the same shape as Y.
Okay, X is the same color as Y and X. Okay. Okay, that makes sense.
Yeah, that helps a lot of people to do it like that.
Okay.
Great. Hey, it's really, really good that you came into the office hour because this is going to help a lot of people.
Yeah, I want to get ready for the quiz tomorrow.
Yep.
Okay, thank you so much for your help.
Thank you so much for taking the time to come into office hours. I'm so glad that you do that. It's always good to see you.
Thank you. Have a good night.
You too.